Okay. Yasuhiro Iwamura from Yokohama City University. I moved from Tohoku University this April. And my talk is about the current status of research and development of condensed matter nuclear science in Japan. Okay, this is a summary, contents of my presentation. Firstly, I would like to review briefly about the Japanese past research from 1989 to 2015. And next, I'd like to present about the current research. And it's a razor point. And current status in Japan. And lastly, I would like to mention about the challenges and directions of future research. Okay, firstly, various types of experiments had been conducted since just after the Fleischmann and Pond's announcement. At the early stage, electrolysis experiments were measured in Japan. And typical one, D2 electrolysis experiments, it's, they detected heat, excess heat, and neutron emissions and transmutations. A typical one is by Professor Takahashi and Dr. Mizuno. They detected excess heat, and Dr. Mizuno claimed nuclear transmutation like this. And also in Japan, especially in the Hokkaido area, Hokkaido University's researchers participated in the experiments using H2O, light water experiments, light water electrolysis. Typical researcher is Dr. Omori and Enyo and Notoya and Mizuno. They detected excess heat, and in addition to the transmutation. This is a typical data. They detected isotopic anomaly from the iron isotope, like this. After that, a new hydrogen energy project was performed from 1993 to 1998. It was a fairly large project in this field, about 3 billion yen, $25 million at that late. And this project was conducted by NIDO, a New Energy and Industrial Technology Development Organization, under MITI, Ministry of International Trade and Industry. METI now, METI at present. And NHE project has two parties. One is energy demonstration team, and the other is the fundamental research team. Energy demonstration team was, they did experiments at IMLA. They did experiments at IMLA, Japan. IMLA, Japan is a Toyota Group company with seconded staff from Hitachi, Toshiba, Mitsubishi Heavy Industries, Aisin Seiki, and the other companies, member researchers performed the experiments. And the fundamental research team consists of university researchers mainly. And they have 4 parties: excess heat party, excess heat team, and correlation group. Correlation means correlation between excess heat and nuclear products, and the nuclear physics and the material science. And they are, the leader is Ota and Takahashi and Kasagi and Sakamoto. But unfortunately, the final report was no excess heat phenomena was observed. So at that time, the result is not so solid, confident. So that project ended 4 years. But after that, during the project in Japan, other type of experiments start. One is these are the hybrid experiments of electrolysis and gas rodding. One is typical. One is Professor Arata's work. He did double structure cathode. So he used sub-nano palladium particles, palladium black, and small particles he used. And he put the palladium black inside palladium cathode and the electrolyte and gas. This palladium black was filled with D2 gas, okay? And this is the data of Professor Arata. In this case, if he used H2O, there was no excess heat, but if he used a D2O, he detected a large excess power. And the other example of a hybrid experiment is Iwamura, multi-layer cathode. He used a multi-layer cathode, and he used electrolyte. Upper is electrolysis, and downside is vacuum. And he made deuterium flow permeation from upper side to downside, and he detected the excess heat and the transmutation. Okay. The other experiments, gas rodding experiments by Dr. Yamaguchi. He presented his results, excess heat and helium production at ICCF3 in 1993. He detected this is an increase of a temperature, and this is the detection of helium-4. And also depermeation with multi-layered metal complex by Mitsubishi Heavy Industry, Iwamura. And this is a D2 gas permeate from the multi-layer cathode, multi-layer film through, and he detected transmutation from cesium to praseodymium. Okay. And next one is gas rodding experiment, and they detected heat, excess power from the metal composite particles, very small nanoparticles. Typical one is Kitamura and Takahashi's work. They detected excess power like this, and also this kind of work was performed by Professor Narita, and he observed the transmutation from this kind of work. And about nuclear fundamental physics, Professor Kasagi observed the enormously large enhancement of DD reaction at the low energy. This is energy is horizontal axis energy, and vertical axis means enhancement factor. Enhancement factor means one is a normal DD reaction. And this point, 10 enhancement means 10 times larger, higher reactions of DD reactions. So he observed if we down the energy, DD reaction rate is increase up. Okay. Especially he observed the palladium and the titanium and palladium and the palladium oxide is a very large, very eminent result. Okay. And I would like to talk about the Japan CF Research Society. This society was founded in 1999 by Professor Takahashi. And now the president is Professor Shinya Narita. And we have about 70 members of JCF. And we have a meeting, and the meeting has been held 24 times, ICCF 1 to JCF 1 to JCF 24. And also we publish the proceedings of JCF meeting. And recently we established a partnership with ICMNS. Okay. Okay, so we go to the current research in Japan. Firstly, I would like to, another NATO project, small one. NATO project at that time from 2015 to 2017 for just 2 years. The member of the NATO project was Tohoku University and Teknova and Kobe University and Nagoya University and Nissan and Kyushu University. We used nanoparticles like this. Nanoparticles are consisting of palladium and nickel and copper and the zircon oxide absorbed H2 or D2 were heated up about 300 degrees and centigrade and observed anomalous heat generation that cannot be explained by known chemical reactions. And we checked the reproducibility for this phenomena. The same sample was divided between Kobe University and Tohoku University, and the same level of excess heat was observed under the same conditions. So reproducibility was confirmed by this NATO project. This is the example of the NATO project results. It is a little bit difficult to see, but excess energy absorbed D or H is larger than known chemical reactions, depending on the conditions. Okay. And also, this is the data for reproducibility. Red one is the data of Kobe University, excess heat, about 4 watt. And blue one is the Tohoku University's data. And these experiments use same samples, same particles, and we performed the same. We have performed similar experiments under the same experimental conditions. And the Tohoku University is here, and you can see that very similar results we got. Same. Okay, and this is the comparison of Kobe and Tohoku, very similar results we got. Also, during the NATO project, we observed new phenomena from this experiment. It's a heat burst. This red line means pressure in the chamber. We put the particles in this chamber, so pressure up. Similar, accordingly, this red and blue one is temperature, pipe temperature, upper side. So we can see a burst-like coincident events of chamber pressure and upper side temperature. So this data can be considered as heat burst occur in the samples and sprout out, and the temperature increase up. Actually, after the experiment, copper nickel zirconium oxide particles adhered on the flange surface, upper side. So it's the evidence of a heat burst we got during the NATO project. Okay. So I will explain about the current research participating organizations, universities, companies in Japan. Universities participating in this field is Kyushu University, Kobe, Kyoto University, Waseda University, and Tohoku University, Iwate University, Yokohama City University, Nihon University, Nagoya University, and Tokyo University of Science. And main companies participating in this field, as long as I know, Nissan, Toyota Central Research Laboratory, Denso Corporation, Mitsubishi Heavy Industries, Technova Incorporation, Clean Planet, and Z Mechanism Technology, and New Hydrogen Fusion Energy. It is a venture company by Professor Takahashi. And hydrogen engineering application and development company is Dr. Mizuno's company. And recently, we know the Cool Fusion venture company. Okay. That's companies now in Japan, companies, okay. And this is the overview of university research. And one is, first one is the Kobe universities. Professor Takahashi was the member of Kobe University, and he initiated and leadership. He has a leadership about these data, and Professor Kitamura performed this kind of excess heat experiment. They use a nanoparticle consisting of palladium, nickel, copper, and zirconium oxide near, like a NATO project, absorbed by H2 or D2 gas, were heated up and observed anomalous heat generation. So they have a relationship with Technova and the New Hydrogen Fusion Energy. And recently, at the Kobe universities, helium-3 in nickel-based metal nanocomposite doped with zirconia, which exhibit anomalous heat generation, was detected by NRA, nuclear reaction analysis, and the TDS, thermal desorption spectrometry. It was mainly Professor Yamauchi and the other colleagues performed this data. So they detected helium-3 after the samples which produce excess heat. And this data shows this one is integrated calorimetric values. So excess heat, amount of excess heat here. And this one is number of D pitch correspond to the helium-3. So we can see that the proportional excess heat and now helium-3 seems to be proportional. So that is a very interesting, strong evidence, I think. And this one is a research activity by Waseda University, Professor Naito. And they use similar sample, palladium, nickel, zirconia particles. And they use a very high speed, high pressure pulse, hydrogen pulse, and like a shock wave. And they detected the excess heat by the collision of a heat shock of hydrogen gas. So this is data of the result. Without hydrogen gas, not so much, very little excess heat, but if they use a hydrogen gas, pulsed flow, shock wave, they got about very large 100, more than 100 watt they detected. And this one is an overview of the Iwate University's results. They use also nickel film and palladium film, and they detected about 0.3 watt, and this is the data for excess power. You can see that they detect the excess power like this. And this one is Tohoku University's results. We use nickel-based nanoscale modulator thin film, preloaded with hydrogen gas, and heated up rapidly to make diffusion hydrogen and induced enormously large heat generation that cannot be explained by any known chemical reactions. This is a data summary. These regions correspond to the chemical reaction. This is a methane combustion and hydrogen combustion here. And this axis means released energy by per fuel, per hydrogen or deuterium. And this region corresponds to the nuclear fission and the nuclear hot fusion here. And they got data, excess power between chemical reaction and nuclear reaction. So at least these data cannot be explained by chemical reaction, okay? And this is another data by Tohoku University, mainly Professor Kasagi did this work, photon radiation calorimetry. He measured the excess heat by only photon radiation. Based on the photon radiation, they get excess heat. In this case, we use some coupled data, and in this case, we use photon radiation. But by the other method, we got almost the same level excess power, about 5 watt. Okay, I would like to talk about recent current TEED project. This TEED project is now undergoing from 2020 to 23 to 2025. But it is planned 27. This is right. 2023 to 2027, 4 years. And the TEED program was funded by TEED, the Thermal Electric Energy Technology Foundation. And it is planned for 4 years. The budget is 0.2 million yen. And title of the project is a New Hydrogen Energy Innovation. And participate universities here: Kyushu University, Kobe University, Waseda University, and Tohoku University, and Yokohama City University, and Iwate University. And objective is the development of new hydrogen energy as a safe and compact energy source. And new results are presented in this conference at the ICCF26. This is the presentation number. Kobe University's data presentation will be today, and also Tohoku University's presentation today, 26P to P3, and tomorrow I will present here, and Professor Narita. And on the 29, Waseda University's presentation. Okay, so lastly, I would like to mention about challenges and directions of future research. So this view graph shows the possible condensed matter nuclear science business opportunities. Of course, you will see that this technology will impact on social change. And condensed matter nuclear science have a feature of compact and CO2-free, and consumption of hydrogen gas is very low hydrogen gas consumption or D2 gas consumptions. So condensed matter nuclear science field have a very large advantages for if it will be commercialized. And this is a possible opportunities. One is a heat source. Maybe it is more likely, it is easiest to realize heat source. Heat source for steel and chemical manufacturers, because steel and the chemical manufacturers consume very much electricity, so it is suitable for this technology. And also, if we control the heat or reaction rate, it will be possible to use a heat source for EV and EV power and ship power and aircraft and drone power like this. It would be impact. It is very important to make development about the mobile style products. And also stationary energy source. Co-generation system for building, for example. So this technology produces heat, and also we would have electricity based on the heat. So co-generation system is good for this technology. And also, it would be possible to use as a household power supply and robot power supply like this. This is the time axis. And then my current understanding of our field, it is my opinion. A lot of experimental results have been obtained, and theoretical clarifications are in progress. But at this stage, in the view of nuclear, experimental results up to now are still weak to declare it nuclear. So acceptance by the academic community and the general public is critical, crucial. So I think that it is my opinion. At first, we should develop the most practical and feasible method based on the previous conducted studies, and demonstrate that the method can be put to practical use. For example, or heat source or other practical application. And if we can achieve 1 and 2, the people in the world would recognize that the usefulness of the research in this field, and the funding will be available to expand the number of researchers. As David and then Alan Smith talked, funding is lack in this field, so we should get more fund. So maybe a demonstration is very important. And after that, we would make a clarification of the reaction mechanism. Okay. So for example, future research issues to clarify reaction mechanism. As a reference, I put a transmutation of cesium to praseodymium. So it's important mass balance between the reactants and products, and match of the expected calorimetric value, excess heat value, with the amount of reacted or produced material. It's very important. But the amount of the element is very small. It's very difficult. And also control, reaction, clarification of reaction control condition is very important, I think, to use this technology. And also construction of establishment of a reaction theory. So I would like to conclude my presentation. So about Japan, research in the condensed matter nuclear science has been continuously and actively conducted in Japan. Experiments on the adsorption and the desorption of deuterium and hydrogen by nano-sized metal composite particles and multi-metal complexes have been the main focus in Japan. And heat generation is observed not only with deuterium, but also with hydrogen. And reproducibility, heat generation, is very good. And heat generation that cannot be explained by chemical reactions and observed excess power implies that it is possible to be a nuclear origin. And as I said, researchers in the field, it's also my opinion. I think that researchers in this field, researchers in the field of condensed matter nuclear science and condensed matter chemistry, which has been lacking so far. Because nuclear physicists and electrochemists gathered in this field, but condensed matter physics, like solid state physics and condensed matter chemistry, which has been lacking, I think. So we should, they should be brought into our community, and systematic research should be conducted to clarify what is happening. At the same time, it is important to demonstrate that this phenomena can be put to practical use as a new energy source. Okay, thank you for your attention.
Okay. Thank you very much. Just a question and comments.
Thank you.
I think that most researchers here noticed that he eluded discussion of interpretation of with D2. Okay? Adding D2 increased mass number 4. That is correct. But adding D2 increased the atomic number 4. I think that everyone knows that, but everyone wants to seek the confrontation with mainstream physics. That is very bad attitude here. We must change the physics society. Okay? No neutron exists as a fundamental particle. Neutron is a pair of proton and electron in deep Dirac level.
Is it a
That
comment?
is very important.
Is it a question or comment?
Yeah, that is a question.
Wow.
Why do every people ignore the real interpretation of his experiment? His experiment clearly shows that the current nuclear model is incorrect. Nuclear is constituted only by proton and electron in the internal electrons. That is the standard theory before the introduction of a neutron by Chadwick. Everyone believed that, but the course is changed.
Excuse me, it's not the much for this their talk there. So
No, this is very, very important.
yeah.
I am very upset because that my paper is rejected.
Okay.
Okay, so
Oh
okay.
no, it's not okay. This is very, very important. Currently, the cold fusion society, cold fusion is a science, but the physics
Yeah.
and the nuclear physics is not a science.
Please stop there. Yeah.
Thank you.
Okay, any other question or comments?
Okay.
Okay.
I fully agree with your statement that we need to see some workable, practical use case of the product. In one of your slides, you showed all the use cases of EV, everything. Don't you think space can be a very good use case for us?
Space.
Outer space?
Okay. I think it is possible. And the application of space devices is very good for this technology because the cost problem is not severe. So I think I agree with your.
And the only problem they have in space is heat, and we are producing heat. So I think it can be a good low-hanging fruit for us to get to space application. Then the funding, everything will come down.
Okay. Thank you.